we started talking about compounds containing two stereocenters or more. We said the total number of stereoisomers possible is always equals to 2 to the power n, where n here is the number of stereoisomers. The previous example, let's just take a new example actually, and let us simply introduce a new phenomenon which is called mesocompound. Let's take 2,3-dibromobutane. When you draw the 2,3-dibromobutane, what you can see, it's like this: CH3, CH, Br, then CH, Br, then CH3. As you can see in here, it's very obvious that this carbon is connected to 4 different groups and atoms, which is hydrogen, brom, methyl, and all of this group. Therefore, this carbon is a stereocenter. Similarly, this carbon is also another stereocenter because, again, it's connected to 4 different groups or atoms. So the total number of stereocenters we have in this compound is equal to 2. So the maximum number of stereoisomers for this compound supposed to be 2 to the power 2, which is in this case equals to 4. So what should we expect in this case? We should expect to see that we can do maximum 4 stereoisomers of this compound. Could be 4, but could be also less. So similarly, let's always it's actually recommended to use what we call the Fisher projection whenever you are dealing with compounds containing more than 1 stereocenter. And the best option to draw the Fisher projection is always to consider the carbon is on the horizontal, the vertical lines, while the other atoms in the vertical ones. So here we have a methyl and then a methyl. And then we have the bromine. The easiest way to draw it like this: brom, brom, brom. Make it opposite first, or trans fashion. So the first stereoisomer which we may draw for the 2,3-dibromobutane is this compound. Of course, the mirror image of this compound will be the same. So we have CH3, CH3, and then Br, hydrogen, Br, hydrogen. So these two, so we have the first stereoisomer, first and second stereoisomers. The relationship between these two are enantiomers. As you can see here, these are mirror images, but they are not superimposable into each other. Similarly, we may draw the other possible stereoisomers, where we have in here, we have, I'm just going to use, here let's just draw the 2 bromine in the same side. And then we will have it actually, if you imagine this is a mirror image, you will have it, it will be very, there is no space actually to draw, so I'm just going to make this smaller in order to have them, the 4 of them in here. So this is the first stereoisomer. Mirror image will be this one. So this is number 1, this is number 2. And then we do have number 3 and 4. So we have Br, Br, hydrogen, hydrogen, methyl, and methyl. Mirror image will be is this one. Now, first of all, let's just remind you what would be the name of the compound of each one. What's the name of the first compound, guys? Can you draw the name of the first compound here? Would you please draw the name of the compound? What should it be? If I ask you name or give AIPAC name of the first compound, what would it be? Anyone knows? Alright, the AIPAC name of all of these must be the same, which is 2,3-dibromobutane. The difference is in the absolute configuration. The first compound, as you can see, let's simply draw or simply assign the absolute configuration of each stereocenter. The first one, this one, the absolute configuration will be the S configuration, and this is again the S configuration. So it is actually the first compound, the AIPAC name of the first compound will be 2S, 3S, then 2,3-dibromobutane. So this is compound number 1. This is the AIPAC name of compound number 1. While compound number 2, since it's compound 1 and 2, they are mirror images, so then definitely must be 2R, 3R, then continue the same, 2,3-dibromobutane. So this is compound number 2, because as I said, 1 and 2, they are mirror images, therefore the difference in the name will be always just the opposite or the inverse of the absolute configuration of each. So if this is 2S, then it must be 2R. If this is 3S, then this must be 3R, because they are inversion of configuration to each other. Got it? This is generally speaking how we name it. So we just apply the ordinary rules of the AIPAC nomenclature, then we must determine the absolute configuration of each stereocenter, then we add them first into two brackets, and then we assign the absolute configuration with its number, then the second one, then the third, then the fourth if there is, and then just the correct name. You follow me? So we'll come to 3 and 4 in a while, but let me just see what's the relationship between 1 and 2. Now 1 and 2, as we said, they are enantiomers, because as you can see, these two structures, they are mirror images, but they are not superimposable to each other. So if you hold the two methyls here and bring them here, you will see that the methyls will be superimposing to the methyls, while the hydrogen here will come over bromine, while the bromine comes over hydrogen. Therefore, they are non-superimposable into each other. So that's why these two structures are mirror images. But what's the relationship between 3 and 4? Would you please interact a little bit? Just use your mic or write down, just in order to feel that you are there. Enantiomers, Ahmed, they are enantiomers. First of all, they are mirror images, Ahmed, right? They are mirror images to each other, because if you place here a mirror, what you will see, this is an image of this and this is an image of that. But the question is, are they superimposable or not? This is the question is, are they superimposable or they are not superimposable? As you can see, 3 and 4, if you hold them from the methyls and you try to superimpose structure number 3 to 4, you may see they are not superimposable. I'm just going to remove 1 and 2 for the time being, and then I come back to them. Although 3 and 4, they are mirror images, but they are superimposable into each other. Do you follow me? So always Enantiomers, for any pair of compounds to be enantiomers, there must be two conditions. First condition, there must be mirror images. But the second condition also must be there, that these two mirror images, there must be not imposable into each other. Because as we said, there are a huge number of compounds or objects. They are mirror images to each other, but they are superimposable into each other. Give me that one. For example, let me see this and that. For example, in here, you can see here, these are mirror images to each other. Do you follow me? But they are superimposable into each other. So it is, they are superimposable into each other. Therefore, what's the relationship of any two mirror images, but they are superimposable into each other? What do we call them? Any two mirror images, but they are superimposable into each other. So they superimpose into each other. What do we call them? Right, but we call them, what's the relationship? What's the relationship between these two? What do you call them? And if I ask you, just define the relationship between these two objects, what would you say? Would you say they are enantiomers, they are the stereomers, they are the same compound, they are different? What do you say about these two compounds? Again, they are mirror images, but they are superimposable into each other. What do you say about these two things? Ahmed is correct. They are the same compound because simply they are mirror images, they are superimposing into each other. So if two compounds, if you have always true, it's always true. Whenever you have two objects and they are superimposing into each other, then they are the same. For example here, see, these are mirror images to each other. But if you try to superimpose into each other, they will superimpose. So if I asked you what's the relationship between these two objects, you wouldn't say that, oh, these are different compounds, oh, these are like the stereomers or whatever, because they are mirror images. It's very obvious that anything which is mirror image to each other and they are superimposed into each other, they must be the same compound. Always remember that. So, mirror images, any mirror images and superimposable, we call them same compound. Now, let's see, as I said in here, 3 and 4, although they are mirror images to each other, but at the same time, they are superimposable into each other. Let us see, and let me prove to you that they are really superimposing into each other. Now, let's rotate, just here, rotate structure 3 by 180 degrees on same plane. You know, what's the rotation of anything by 180 with the same plane? For example, this marker, if you want to rotate it by 180 on the same plane, you rotate it like this. If you want to rotate it again by 180, you rotate it like this. Again, like this. Do you follow me? This is simply the rotation of 180 on the same plane. Do you follow? Again here. If you have this object, you want to rotate it by 180, you just rotate it like that. Again, so the one here which was above here becomes below. It becomes this side. Again, focus. You see, this is the rotation of 180 on the same plane. So let us rotate structure number 3 by 180 on the same plane. All right. So in this case, what we are going to get here, just for the sake of identification, for the sake of making things easier, imagine that this is carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4. When you rotate this here by 180, the one which was above the plane here will become below, and vice versa is true. So in this case, we are going to get the 4 is here, this is CH3, but this is 4, and this is 3, and this is 2, and this is 1. Do you follow me? This is always this rotation. Is that clear, this rotation, what I mean by rotation? By 180 on the same plane. Now, when you take this way, the bromine which was to the left side, they will become to the right side. And the hydrogens are vice versa. Is that clear? Can you imagine? Is it clear now how to rotate structure number 3, just rotation, by 180 on the same plane? Is that clear? All right. Now, as you can see, this is just a rotation of 3. Now, of course, now, when you do this rotation, try now to superimpose. Let us just imagine that we took this, we hold this from the methyls, and we bring it to structure number 4. What you see? When you hold the structure from the methyls and then bring them to, and try to superimpose them into structure 4, you will see that every atom will superimpose with any other atom. In other words, the methyl will become over the methyls, the bromine over the bromine, the hydrogen over the hydrogen, which means structure 3 and 4, they are mirror images, but yet they are impossible into each other, and therefore structure number 3 and 4, they are same compound. Do you follow me? Is that clear? Is there any questions so far? All right. So this case here, in this case, this type of compound, when we have, check again, this type of compound, it has actually 2 stereocenters. Now, any compound, this compound, we call it actually meso compound. And the meso compound, it's a compound contains more than 1 stereocenter, but it is achiral due to the presence of plane of symmetry. So, how to identify any meso compound? Some compounds, although they have a stereocenter, more than 1 stereocenter, but we call them achiral. Now, again, let me just remind you with the fundamental issue of this chapter. When we say chiral compound, means there is no plane of symmetry, which means the object and its mirror image, they are not superimposable into each other. Do you follow me? Like my right hand, my left hand. So they are chiral because the object and its mirror image, they are not superimposable into each other. While we still have plenty of objects where the object and its mirror image, they are superimposable into each other, therefore we call them the same, because simply there is a plane of symmetry. You can imagine the plane of symmetry in here, it's like, a plane which can divide this object into 2 halves. But in the case of my hands, there is no plane of symmetry. I cannot find a plane of symmetry which divide my hand exactly like two halves, because if you imagine the plane of symmetry would be in the half of the hand, the above hand here will be different than the below, and therefore there is no plane of symmetry in the chiral compound. Now similarly, for meso compound, it is a compound which contains more than one stereocenter, but it is still achiral because it contains a plane of symmetry. Where is the plane of symmetry in this compound? It's very obvious that the plane of symmetry of this compound is this plane of symmetry. You can see it here. You can imagine that if you have a plane here, you allow it to pass through the half of the compound, you will see you are going to get two identical halves, and therefore this compound, although it contains two stereocenters, but still we call it is achiral, and which means the object and its mirror image, they are the same compound. So they are not isomers. Do you follow me? So that's actually always, whenever you have a plane of symmetry, be careful. If the compound contains a plane of symmetry, the chirality will cancel, which means the object and its mirror image, they are the same. They are not enantiomers. Do you follow me? They are only enantiomers if there is no plane of symmetry in the compound. So this is actually after we have introduced. Is that clear, guys? In order before moving ahead, is that clear regarding the meso compound and the definition of meso compound? Any question about the meso compound? All right, perfect. So let's get back to our whole principle, our whole example, what we have discussed so far. Our example was 2,3-dibromobutane, and we were trying to identify all possible stereoisomers of this compound. We have seen for the 2,3-dibromobutane, we have seen first one is this one, sorry. The first stereoisomer was this Br, hydrogen, methyl. So this is structure number one. It's mirror image because they are not superimposable into each other. CH3, Br, hydrogen. And the third compound, which is the meso compound, because we said it is achiral compound. So as you can see, for 2,3-dibromobutane, we have only 3 stereoisomers. Do you follow me? Not 4. Not like the previous example which we have discussed in the previous lecture. In the previous lecture, we have discussed an example which was called 2,3-dibromopentane. So there is no plane of symmetry in the 2,3-dibromopentane, but for 2,3-dibromobutane, we do have a plane of symmetry, and therefore the total number of stereoisomers possible for such a compound is lower than the maximum which we are expecting, because if you remember at the beginning of this lecture we said the maximum number of stereoisomers is 2 to the power 2, which is equals to 4. In reality, what we found, we found only 3 stereoisomers possible of this compound. So which are they? This is number 1 and 2 and number 3. Now let's define the relationship between these. Yes, please.
What if we get the mirror image for the third one?
It's actually, look here. The third one here, it has a mirror image, but the third one and its mirror image, they are the same. They are identical. So there is no meaning to always to draw or to write the same thing twice, isn't it? Do you follow me? we only draw another structure. We don't draw the same thing twice or 3 times or 4 times. It's the same. There is no meaning if you draw the mirror image of this. Do you follow me? The one who asked. Yes, go ahead, sorry.
But the bromine will be in the another side.
Yeah, but I have explained, because this, if you make a rotation, do you follow me? It will be the same like the previous one. Let me just again make it. All right. Okay, so please focus with me again. So let me draw the mirror image of this. What's the mirror image of this? The bromine will be on the other side, isn't it? So this is bromine, bromine, and methyl, methyl, hydrogen, hydrogen. This is what you want, right?
Yes.
Perfect. Now, what I'm saying, these two compounds are same. These two compounds, there is no meaning to draw them twice because they are the same. Why they are the same? Because they are mirror images, but yet they are they are superimposing, superimposable, superimposable. Do you follow me? Why they are superimposable? Of course, they are mirror images. I think everyone knows, and I think you can just guess. They are mirror images because if you place a mirror here, you will see this is the mirror image of that, isn't it? Do you follow me? Keep talking to me in order to, to know that you are following me. Hello? The one who asked, keep talking to me, please.
Yes, it's clear now.
All right. Now, let me just finish. So they are mirror images, but they are the same because simply, as I said, if you make a rotation now, make rotation by 180 on the same plane. Remember, it must be on the same plane. When you make a rotation of this, what you're gonna get, you are going to get CH3, CH3, bromine, bromine, hydrogen, hydrogen. Is that what you are going to get or not?
Yes, the same.
Do you follow me? Now let's see, which is simply rotation, just any object, if you rotate this object this way or that way or any rotation, it's the same object, isn't it? Hasn't been changed, right? Now, let's see, is this object, the rotated object here, is it superimposing with structure number 3 or not? Just hold it from the methyls, bring it here. What do you see? What do you see? They are superimposable. So therefore, there is no need to redraw or to draw the same structure twice or 3 times or 4 times, because the same structure we draw it only once. We only draw different structures if they are different. But if they are the same, then we don't draw it. There's no need to draw it more. Do you follow me? So that's actually why, now you see here, why this and that they are superimposable, although they are mirror images to each other, due to the presence of plane of symmetry. Always presence of plane of symmetry will, let's say, cancel the chirality, will damage the chirality. Do you follow me? So therefore, the object and its mirror image are superimposable in this case. So let's get back to all 3 stereoisomers. Is there any questions before moving forward? Please, if there is any question, ask now in order to move forward and then to talk about something new. Is there any question about the meso compound? Any question? Okay, clear now? All right. So let's move now. Let's again back. Just redraw all possible stereoisomers for the 2,3-dibromobutane. As I said, we only have 3 stereoisomers for the 2,3-dibromobutane because one of them is achiral. So we have the Br, hydrogen, hydrogen, CH3, 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 hydrogen, Br, hydrogen, sorry. Yeah, this is Br and this is CH3, and the third one will be Br, hydrogen, hydrogen, CH3, CH3. So we have structure number 1 to structure number 2 and structure number 3. As we said, 1 and 2, they are enantiomers. And now what's the relationship between 1 and 3? So let's again here, write it down. The relationship between structure number 1 and structure number 2, they are enantiomers. Right. What about the relationship between 1 and 3? Or 2 and 3? What's the relationship between 1 and 3 or 2 and 3? What do you think? What should it be? If you remember from the previous lecture, yes, perfect, thank you, perfect. If you remember from the previous lecture, if we do have two stereoisomers which are not enantiomers, then definitely they are diastereomers. So then definitely the 1 and 3, as you can see, 1 and 3, they are not enantiomers, but they are stereoisomers, then the relationship must be then diastereomers. And the same thing applies to here, diastereomers. That's always the case here. If the relationship, if they are not enantiomers, then if we do have stereoisomers which are not enantiomers, then definitely they are diastereomers. Do you follow me? That's all actually about stereoisomers, enantiomers, and so on and so forth. Let's now move to one specific issue which we call it, actually we will get back to it because we have skipped it for the time being because I think always it's better actually to talk about it later on, which we call it specific rotation, the alpha D of the compounds. Is there any question? Is there any question? Yes?
When we have to rotate the structure so we can say that they are identical, when we don't keep them as they are and say that they are not
I'm really sorry, I didn't hear you. Actually, the question was not clear. Repeat the question, please.
When we have to rotate the structure so we can say that they are identical, when we don't keep them as they are.
Was your question about structure number 3 and 4 or 1 and 2? What was really your question, or what you exactly want to ask about?
The same question as the one I said previously.
Yeah, what about them? For example, 1 and 2, what you want to ask about them?
I mean, when we have three isomers.
Why we have 3 isomers?
Yeah, when we have to rotate the structure. So
Because they are different. Because the spatial arrangement of the atoms in this structure are different. For example, here, this structure is different than this. You see, the bromine is to your right side, the hydrogen to your left side. Here, the hydrogen to your left side, the bromine to your right side. Do you follow me? So these two structures, they are not identical. They are different. Do you follow me?
Yes.
That's why actually we have to draw them different structures, different stereoisomers. That's why we said for any compound contain n stereocenter, there is a maximum of 2 to the power n stereoisomers, and these are the stereoisomers which are possible for this compound. Do you follow me?
Yes.
So did I answer your question, or this is not really your question? when we have to rotate the structure?
Yes, and why we rotate them?
All right, it's only just a method to prove to ourselves that these two compounds are the same or they are different. Yeah, that's a very nice question actually. Now, the 1 and 2, if you rotate any one of them and you find the result of the rotation is superimposing on the previous one, then definitely to write them as enantiomer is wrong because they must be the same. Let's prove to you that whatever, regardless of the rotation you do, 1 and 2 will never ever superimpose. Do you follow me?
Yes.
Right. Now, what you want now? Let's make a rotation of 1 and 2. For example, let's rotate 2. Let's rotate 2 by 180. What you gonna get? So let's rotate it by 180 degrees on same plane. Do you follow? Always remember that. Actually, I'll tell you later on why on the same plane. When you rotate it, you are going to get this one, CH3, CH3, and then bromine here, right? And yes, bromine here, hydrogen there, and then bromine here, and hydrogen there. Oops, isn't it? Yeah, true. Isn't it? Because simply you can see, imagine this is 1, 2, 3, 4. When you rotate it, the one becomes here 2, 3, 4. Now, number 2 was the bromine to your right, so number 2 becoming the bromine to your left. Number 3, the bromine was number 3 was bromine to your left, then it will be to your right. So this is the new structure after rotation. Hold it from the methyl and bring it there, they will never superimpose. Do you follow me?
Yes, sir.
Now, just to make the story short, we do the rotation just to prove to ourselves if these two structures are the same or not. Do you follow me? So, regardless of the rotation, what you do, the structures must never ever superimpose. If they superimpose, then they are the same. دائما remember that whenever you have two mirror images to each other and they are superimposing, that means they are the same. Now while we do rotation, we just do rotation to make it easy for us to imagine, because we don't have the models, we don't have the three-dimensional structures. All what we have the two-dimensional, which we draw on the board or we draw it on the paper, but we have to imagine. We must imagine, try to imagine the structure in the three-dimensional in order to be able to answer the question: are these two mirror image structures, are they superimposable into each other, or they are not superimposable into each other? Because if they are superimposable, that means they are the same. If they are not superimposable and yet they are mirror images, that means they are enantiomers. Got it?
Yes, sir.
Perfect. Wonderful. Now let's go back to something which is about what we call the specific rotation of a compound. Specific rotation what we call it alpha D. Now, whenever you have enantiomers, for example R and S, for example, and you want to check their physical properties, what you will see, this is R, this is S, and these are enantiomers. The boiling point, suppose this is 112.3, you will see that this is 112.3. The melting point, if this is suppose 57.12, this will be 57.12. Solubility will be same. Most of physical properties, they are the same. Generally speaking, enantiomers, they have same or identical, let's say it, physical properties. And for example, if you remember in the lab or in the demonstration of the lab, we had discussed what we call it the simple distillation and the fractional distillation, and we said the distillation actually we can always separate the compound by distillation, or we can separate liquids by distillation depending on the difference of their boiling points. Shayma, what do you mean by slowing down? What do you mean by slowing down? Is there anything which you don't understand and we are in hurry, or what exactly the case? Shayma. I am slowing down. If I am slowing down, then just ask. Writing the board. Okay, now anyway, all right, I will slow down. Okay, now again here, as I said, don't worry about Shayma if you couldn't write, if I erase what I'm writing very fast, because as I said, there will be always, the video will be recorded, so don't worry, you can always see it. Now, anyway, let me get back to the physical property and the importance of the physical property. Now, when we have two compounds, they have different physical properties, we can separate them. For example, if you remember the liquids which we want to separate them by distillation, we said we can separate liquids or different liquids by distillation if they have different boiling points. Now, if we have solid compounds, different solid compounds, we can separate them by crystallization because they have different solubility. Do you follow me? But in principle here, enantiomers, they have identical physical properties. So, how they differ? How could we, as chemists, how could we identify them if they simply have the same physical property? They only differ in their rotation of what we call it plane polarized light. Let's from now on use this abbreviation for plane polarized light and write it PPL, plane polarized light. So, what does that mean? If one of them rotates the plane polarized light by, for example, if the R compound rotates the light to the left by, for example, 35.23 degrees, then this must be rotating the light to the right by the same angle, 35.23. Or in other words, if the alpha D, which is the plane polarized light, I will talk about it in more details just a bit. If this is here plus, suppose, let me write it, minus. If this is here minus 35.23, this is here will be plus 35.23. So this is the only difference of enantiomers. Enantiomers only differ in the rotation of what we call it plane polarized light. I will explain now the meaning of the plane polarized light, but I just want you to focus on this board because that's actually the summary of the whole issue. That enantiomers, they have identical physical properties, they only differ in the rotation of the plane polarized light. If one enantiomer rotates the plane polarized light to the right with certain angle, the other enantiomer must rotate the plane polarized light to the left with the same number or the same degree of rotation. Do you follow me? That's actually, now let's just define to you or just explain to you a little bit about what we call it the polarimeter and the plane polarized light. In principle, whenever you have ordinary light, this is the light, ordinary light. This light will always oscillate in all perpendicular directions. Do you follow me? So this light, you can see it, any light in this room, for example, you can see it from all directions. But if you allow this to pass through certain prism, it will be changed into something called plane polarized light. Plane polarized light. What's the difference between plane polarized light and the normal light? The difference is that the difference between plane polarized light and the light you can see it from all directions, but the plane polarized light you see it only if you are on the same plane. In other words, you can't see me because simply the light is simply falling on me and it oscillates in all directions. So it's not necessarily that you sit exactly opposite to me in order to see me. You can see me from all directions because simply the light on me will oscillate from all directions or in all directions. But the plane polarized light, it only oscillates on one direction. In other words, if my hand is a plane polarized light, it's a sort of plane polarized light. What does that mean? You only can see it if you are in this plane. Do you follow me? This way. If you are this plane, you will never see my hand. That's the only difference between what we call it plane polarized light and the light. So in this case here, this plane polarized light, if we allow it to pass through a sample or a container containing active or what we call it a chiral compound, and one of the enantiomers, this light will be shifted, will be rotated a little bit. It will be like this, for example. It will be rotated this way from its original place. So if you are viewing here, if you are looking at this plane polarized light, what you will see certain rotation of this plane polarized light. Do you follow me? This rotation, this is what we call it the alpha, is the degree of rotation of plane polarized light. So this alpha is degree of rotation of plane polarized light. So, in principle, in order to use this property as a measurable one, we use or we introduce the alpha d, the specific rotation. This is called specific rotation. And the specific rotation is always equals to alpha over c times L. And alpha is, well, this is actually what we said. The alpha is the degree of the rotation of the plane polarized light. But the C here is the concentration of the sample in gram per milliliter. And the L here is what we call it the length of the tube, or this sample, the length of the tube, and it must be in decimeter units. And remember that the decimeter, every 1 decimeter is equals to 10 centimeter. Now if you check your slides and you see, for example, the table 5.1, for example, in your slides, you can see, for example, the alpha D of several compounds. For every chiral compound, we have its It's alpha D, it's like, it's like a characteristic, physical property of this compound, which we use it to identify it in the future. Do you follow me? Now, take the example here, the work example in the slides, just to use it for the alpha D. Suppose 1.5 gram sample, 1.50 gram sample has been dissolved in 10 milliliter ethanol and placed in a sample cell with 5, and the tube or length of the tube of the polarimeter is equal to 5 centimeters. The observed rotation alpha, only the alpha, is equals to 1.21 degrees. Calculate alpha D. To calculate alpha D, it's very simple actually. All what we need to apply in the rule here, and the alpha D is equals to alpha over C times L, which equals to the alpha is 1.21 degrees over the concentration here, which was, we had 1.5 gram dissolved in 10 milliliter. The concentration here then, it will be the 1.5 gram over 10.0 milliliter, which equals to whatever. So this is simply the concentration, which is equals to 0.015 gram per ml, because that's actually what's supposed to be. Do you follow me? So it is over 0.015 gram per ml times the tube, the length of the tube, which is 5 centimeters, which is equals to 0.5 decimeter. That will be the alpha D of the sample, how we calculate or how we convert the alpha into the alpha D. So it is straightforward issue, the alpha D and the alpha, but as I said, the alpha is just, the alpha D is like a standard physical property of the compound, which we use it to identify compounds from each other. Now, if the plane polar, again here, just to make the story short, enantiomers, they only differ in one physical property only, which is their interaction with the plane polarized light. If my right hand is one enantiomer and it rotates the plane polarized light to the right by 30 degrees, then my left hand will rotate the plane polarized light to the left by again 30 degrees. Do you follow me? That's the whole issue about what we call it specific rotation. So that's why actually rotation of the light to the right we call, if any enantiomer rotates the light to the right, we call this enantiomer dextrorotatory. We call it dextrorotatory. And similarly, if the enantiomer rotates the light to the left, we call it levorotatory. The levo in here and the dextro is just some Latin words. The dextro means right and levo means left. This is simply what we use in this type of properties, levo and dextro. To make the story short again, enantiomers, they have identical physical properties. They only differ in their interaction with, we call it plane polarized light. If one enantiomer rotates the plane polarized light to the right, which is always we give it plus sign, then the other enantiomer must rotate the plane polarized light to the left, which is we give it the negative sign, but with the same type, with the same degree of rotation. Do you follow me? So plus 30, that will be minus 30. This is plus 500, that will be minus 500. That's the whole story about the different physical properties of enantiomers. Is that clear so far about enantiomers and about the specific rotation of the compounds? Is there any question about it? Is there any question so far? Perfect. I think it's enough for now because we will have another lecture at 2:15. So our next lecture, in order to compensate for the last one, we will have another lecture at 2:15. And then at 2:15 we'll continue discussing chapter 7 in the edition number 9, which is the alkene, the nomenclature and its reactivity. There will be no lab this week. No, will be no lab this week. No lab for this. We will use the lab of this week just to compensate for any loss of lectures, because we will use actually today's lecture in the lab and as well to Wednesday lecture in the Wednesday. Yes, there will be no lab this week, but only there will be lecture. So I'll see you inshallah at 2:15. We will continue our next lecture. All right? See you then. Until then, see you. Have a good day. See you.